joined again by our friend and colleague, Dan Ambre from Full Spectrum Diagnostics. We got a few minutes here. Let's give a few minutes while we got a couple people. We have quite a few attendees that responded that are going to be joining us. So we'll give them a minute or two here to jump on the webinar. While we're waiting, just a couple housekeeping items. We are recording this, so if you nod off or you need to take a break, feel free to. And we will be sending out a recording of this webinar, and it will also be posting something out to YouTube here in the next couple of days. So you can always go to our YouTube channel, Vibrant Technology, and look at this webinar and recordings of all of our past webinars too. There's, gosh, I don't know how many are out there now. We've probably got 20 something out there, in addition to many different training courses on all the different Vibrant products and MEscope products. So you can feel free to take a look at that when you get a chance. Let's see here. What else, Dan? Anything else we want to touch on before we jump in here?
No, I think it's been, the seminar was billed as doing case histories, and we have some pretty fascinating case histories this time around. I have 3 of them lined up. I think I only have time for 2, but we'll see if we can squeeze it in.
Great, great. Well, we won't, I believe, yeah, the title is Pipes, Pumps, Fans, Motors, and Turbines, or Turbines, I should say. So we will see how many we get to. If we don't get to any of them, certainly we can touch upon some case studies at a future webinar. These always seem to be more of our popular webinars. So if you folks have additional webinars you'd like to hear or like to see us do, feel free to drop us a line, and we'd be happy to take a look at it and see if we can't pull together something for your needs. Incidentally, if you have questions during the webinar, we like to hold off on answering questions until the end of the webinar, but you can type in your questions in the GoToWebinar box there on the right-hand side of your screen, and we can get those questions answered at the tail end of the webinar. Did want to mention something also about MEscope licensing. There's 3 different ways that you can purchase MEscope products, and this goes for all of the MEscope products, ODS videos included. There is a way you can purchase it on a perpetual license, on an annual license, which works out to about 50% of a perpetual license. And then additionally, we have a monthly license. So you can go out to our website and say you want to just kick the tires for a month on ODS videos. You can get a monthly subscription to the ODS videos, including a lot of our other products as well.
Or if they want to go to a modal and ODS seminar taught by me, you get a 30-day license for doing that, and you get a fully kick the tire type thing for the software as well.
Perfect. There you go. Great. Well, yeah, let's go ahead and get started. We got about 20 so attendees in there, and without further, I will hand things over to you, Dan, and we'll get going here.
Well, good morning, good afternoon, whatever it might be for everybody. My name is Dan Ambre from Full Spectrum Diagnostics. We got a few case histories this week, some interesting stuff that came in, and what I mean when I say came in, I do some work for a small fee. People send me their videos under the right formats. I process their videos and give them a first, just a rough look at it. So you can see how it turns out. This first one's just like that. Somebody from a power plant in California sent me a problem. They weren't sure what to do with it, but it turned out that, they didn't want to rebuild this fan, but they're going to have to. So things like that give you a little bit of insight. Usually the ODS videos is a first look in that first jump over the fence to see if there's anything on the other side. If not, you move along. If so, then maybe you want to go to a traditional ODS analysis and with accelerometers and get a 3-dimensional look at it. Remember, the video clips are 2-dimensional. You get X and Y. You will have to take more than one direction to see X, Y, and Z. how much is in each view. You know, that's the way the video format works, and we'll have a little bit more on that as we go along. So many production-based machines and drive systems can't be shut down to interpret to complete a modal analysis. In these cases, operating deflection shape can provide insight into the motions of the machine during normal operation that can't be readily otherwise seen or interpreted. What we have here is ODS videos. Okay, MEscope ODS videos. It's a high-speed video vibration analysis. Video clip is processed with something called the optical flow algorithm. It enhances the subtle displacement, rescales the amplitudes, and the processing allows the user to see what the human eye can't perceive in a video animation, either because the event's too fast, the displacements are too small, or you get a combination of both. Okay, so we're going to process and see what's going on. This time, and I've never really done this before, but I'm going to, for some reason, I can't advance. What's going on here? There we go. Sorry about that. This unit's asset description. It's a Buffalo Forge induced draft fan, and it's in a boiler house in a power plant. More specifically, there's a video clip shows the outboard bearing sleeve bearing. Okay, you have some water cooling lines coming in and out of it, and what happened was one of these lines plugged. He started eating up the bearing, and then the shaft works its way through the Babbitt material into the journal housing and makes a mess of things. This fan is over 30 years old. It's never been disassembled. It's been running for 30 years. They have this current problem that came up. And one of the reasons they're got some heartburn about this one is what you see on the outside here. This is all asbestos. So they have major controls on this substance in most of the country, especially in California. So that would involve pulling a lot of asbestos out, and they haven't been ready to do that for quite a while. I wanted to show you what this looks like. So this is the raw video, and there's a couple of things that are interesting about it. Number one, you get as it goes up to speed, the frame rate in the cell phone, you get a kind of a really low frequency, and then you see it goes into what you're looking at right now. You really can't see the motion, even though this is pretty low frequency. It's 300 RPM. What you can see out of this is the background here. This is 2 times line frequency. So this is your lights in your power plant are flickering. There are ways to eliminate that. We have background noise removal that we've already applied to something like this, but just so you see what you have. You hear a sound, it just changed as you start up and as you stop the frame rate. So what we do in a situation like this, we have a frame rate of 240 frames per second. This is a slow-mo mode in the phone. So as you turn it on, it goes up to full speed, basically the frame rate, and it takes a couple of seconds. And then as you shut down, it does the same thing. So it's part of the cell phone, easily remedied by just taking a chunk of data in between. So I usually take about 15 seconds worth of data. And I tell people, hey, if you're going to send me a clip, it's got to have, if it comes from an iPhone, fine, set it for a frame rate of 240, 1080p HD for resolution, and the video mode should be slow-mo. And that's what you should record in. If you only use 30 or 60 frames per second, it's not fast enough. And we're going to cut off our data. We're not going to be able to see higher speed motors that way. Anyway, before MEscope ODS video processing, the vibration was elevated to a plugged cooling water line. As the unit heated the shaft, it ate its way through the Babbitt and into the bearing housing. The shaft journal was extremely scored and unusable. A contractor was brought in to machine and sleeve the existing journal to reestablish the OD, and he did a pretty good job in the location that he wanted, just across the bearing. It was pretty straight and even, but there was an internal shaft bend that there's nothing you could do about. So from there's a taper as the shaft tapers down from 8 inches down to 2 inches to accommodate the bearing, and that's where it was bent. And they didn't machine that part. So they're going to have to tear it all down, open it up, rebuild it, and put it back together without the asbestos. Anyway, I just wanted to show you that. So as you go up, you can see some low frequency, you can see some high frequency 2 times line, and this all slows around because we're up to 240 frames. As we shut down, see if I can do this. It changes tone a little bit, and you get it runs down to 0, the end of your clip. So turn that off in the software. As far as we'll take 15 seconds, we'll take 13 seconds in the middle or whatever, and so we don't see that on the ends. Same thing here. This is something different. So it had some low frequency as like you were walking around with the camera, and then it goes to high-speed video is what you're seeing right now, and you're seeing that needle move up and down. If I asked you what is the highest vibration in this field of view for the second clip, you'd probably say the shaft, you'd probably say the bearing housing's moving. Actually, it's this needle. Remember, ODS videos is XY, it's 2-dimensional. Anything moving. If I had a light flickering, that's the biggest vibration, like up here, 2 times line frequency would probably be the biggest peak in the spectrum. Over here, I have this thing bouncing up and down. It's looking for the eccentricity of the shaft. So every revolution, it'll move the needle. And the needle moves, and this is a 300 RPM. So every 300, 0.2 of a second, you get a flutter of that needle. And that's the biggest vibration. So if we're actually have something else to look at, we need to remove the background, make this a background object, and then we won't see that in our data. And I'll show you what I mean in a minute. This is what startled the people in the power plant. This is the turning speed of the shaft is at 300, and it's an axial vibration that's occurring. Why is that doing that? There we go. So mostly axial, a little bit of twist to the bearing housing, and the reason for that was this bend in the shaft. The resulting measurements, they had 14 mils of runout, which exceeded the maximum for the bearing that was supposed to be 6 or less. The radial vibration was 4 inches per second. I don't think that's a very good place to run. And the axial movement was near 10 mils of motion. And we're set up right now so that we see the axial position of the bearing, and we see vertical. So coming out at us would be the third axis that we really don't detect. So our brain tries to put it together, but mostly we're just seeing this horizontal motion in the axial direction of the machine and a little bit of lifting. If we look out here, the shaft's following it. So there's some kind of bend that's causing that type of motion. This is right after the MEscope was processed for the first time. We see the top data, which is the time waveform. We see the bottom data, which is the FFT down here, or DFT, digital or discrete Fourier transform. Okay, so that's the spectrum. This is the waveform. I'm showing, hopefully trying to show both of them. So the time waveform is going to pick up all the little wiggles and things in the spectrum. It's the full view of this. So any wiggles in the waveform are going to be picked up. It's all simultaneous. Down here, when I put my cursor on 1 times RPM, so the 300 CPM there, I will get a filtered response of just what's at 300, and none of the other harmonics or anything going on. So this is more of a filtered vibration analysis. This is interesting. And I'm going to get both of these going here. Remember I said the needle was the highest vibration. In this case, every time that shaft turned 1 revolution, it was banging what looks like what's going on. Is the little spring in there bouncing around? Yes, but in a video representation, this is moving the most of anything. And I get this real low frequency wiggle going under here, and the high frequency every time the eccentric side goes through, I see an impact. Right, it's not really an impact, but it's causing that needle to move. And the same thing up here. All these little things, they're spaced at 0.2 of a second. If you do the math, that's 300 RPM. And you're seeing that wiggle every revolution of the shaft. And that shows up on our dial indicator. So conclusion, ODS video analysis to find elevated vibration at 300 RPM in the axial shaft direction. This suggests potential faults such as a bent shaft, cock bearing, journal, or a significant looseness condition. Notice the things up here, bent shaft, cock bearing, looseness. These are things that can occur in the axial direction, and that's basically what I saw. So they send me a video clip like this. I throw it into the software, process it, and tell them what I see. If they need another view, or I think they need another view, I'll tell them to go take some more data and send it to me. I'm missing something. But normally, if you're out there doing this type of work, you'd want to do horizontal, vertical, and axial as much as possible, just to get a good feel for how everything's moving in the machine. So the dial indicator indicated 14 mils of radial runout and 10 mils of axial runout. Traditional vibration analysis performed by the plant guy, 4 inches per second. Very large vibration. So this is the kind of stuff in this case that stops the room from breathing for a minute when you realize, what's really happening here. Okay, that's the first one. Got a couple more here. This one's pretty cool, and never experienced this before, but it's pretty cool. So ODS videos again. We're doing this optical flow processing of our video clip. Our machine today is this tower, and it's a concentrating tower. This is a sugar refinery. So they're taking, they're making the heavy syrup into something else. And I'm not sure exactly how it works, but there's just flow through this. So there's pressurized flow going through it. It's separating as it goes down the tower. And there's some other things that are going on. There's no machinery on this tower. There are no pumps, there's no fans, nothing, just piping. And from the adjacent building, they're pumping in, the volume of sugar slurry as much as they can. And as it goes through here, it changes state into more of a crystallized form. I'm not a sugar expert, but that's what I gathered from this. Now, for scope of size, these are I-beams, and these are basically a 12 by 12 I-beam. And from the base concrete block up to the top is 70 feet. Only way to take this data is with a boom lift. And we took data every 3 feet up to, actually we couldn't get the boom to go any higher than about there. So about 20 measurements up to here. On each of these beams, as much as we could get to. We also did basically boxed in this platform here, so we could see how the whole platform is acting like a floor, and the same thing up there. So there's maybe 20 locations all the way around the upper platform. So you put it all together, and you get some good data. In the videos, you just stand back in the parking lot and you get an overall shot, you get some close-ups, you try to get all the directions, the perpendicular directions, and see what's going on here. This is the first video. And you got to look at it for a little while before you see what's going on. And this is in the time waveform. So I didn't pick a frequency to look at. I'm looking at what the waveform is telling me. And it looks like these two cylinders are in phase with each other. They're moving side to side. So the free flow of air is going into the frontal face of these cylinders. And some process is going on called vortex shedding. At least we think so. So this unit performs a concentrated refining process. There's no rotating equipment in the framework platform or any internal agitation. The only source of vibration is internal turbulence in the process itself or wind loading that might induce unstable vortex shedding around the tanks. And we'll get to what vortex shedding is in a moment. Here's my setup for the iPhone. Again, it's the highest frame rate we can get, slow-mo presentation mode. And the analysis summary to this point is there's definite frame and tank motion. The animation source was likely a random wind gust created by vortex shedding, and the amplitudes surprisingly were very small. During the day, the wind changed abruptly, and we were on the boom lift still, and it was about 20 feet in the air, and the lift was good for 28 miles per hour. We decided to cut some of our data collection short, but we did capture everything we needed to get a good representation of what this is. Okay, so this first part is all video analysis. Oops. There we go. So you can see all that motion in the towers. Vortex shedding is a phenomenon where the wind blows across the structural member, usually across a circle like this or a cylinder, and vortices are shed alternately from one side to the other. So if you look here, if you drew a sine wave around all these things, when it's shedding like this at a certain prescribed frequency, this is going to be your driving source to inducing a natural frequency or a resonance condition inside your cylinder. And I believe that's what's happening here, at least up here, part of this. Okay, so there's really no bending in the piping around here. We really couldn't measure it anywhere anyway. So all the way up here, with the wind blowing by, we get some different directional response. Over here is a little chart for a cantilevered beam. And you can have a cantilevered beam of a certain length, you'll get a natural frequency. And this is the first bending mode. Okay, it goes to 0 at the base, but it can swing left or right. I just turned this presentation on its side so we can see a vertical cantilevered beam. Second bending mode looks like that. Third bending mode, you get another wiggle in this case, the 1 by 1 foot, 70 foot I-beam. Okay, so if you do get vortex shedding, it sets up a condition where you can excite natural frequencies in the framework, and we're going to show you what that looks like next. Okay, but it can be really damaging to the structure. I took a lot of data, different camera shots, going, all the different directions and the corner directions and everything. The one I found most useful was this one. So I walked up to this I-beam and tipped it all the way up so I could see this upper portion of the structure and see what the beam is doing. And you can't see this when you're there. I processed it and I was pretty surprised at the motion. And if they're, at this company looking at the motion here, that's going to scare them a little bit. So we did do some actual accelerometer measurements so that we could see what the level actually is, and we'll get to that in a second. What this is, a definite frame and tank motion. It's 120 CPM or 2 hertz. That's the frequency of the occurrence. The animation source was likely random wind gusts, and amplitudes are considered small. Okay, there's another mode. There's a whole cluster of little modes down at the low frequency end of the spectrum. This one's definite frame and tank motion, 180 CPM. which is 3 hertz if you're a hertz guy. And this is in the alternate direction. So it's not going in the direction that we just saw. It's going more in the kind of cross corner look at it. If you look up here, the platform at the top, it's more of a lateral motion around the building. This is the beam behind that. So it's closer, one of the 6 beams that's closer to the building. So it's 180 CPM, 3 hertz. And again, it's not flexing this beam as much, but it's more of a rigid body corner to corner motion. Okay, so really interesting stuff. And I think they were really surprised with it. The thing that I can't define directly is how much wind is there and when it occurs. Right now, the plan is to put a permanent monitoring station right at the top of this tower in the corner. And if we use a triaxial accelerometer, we'll be able to see what all 3 directions are doing. So we could get amplitudes, frequencies, time waveforms, whatever the format is that would be good to see, and see what this phenomena is, then maybe it'll give us a better idea how to fix it. Now, since we had an idea that something's going on, it looks like there is a natural frequency in this platform structure, at least 3 of them that we measured or looked at, but they could be amplified. So one of the big pieces that's missing was how much wind is required to get this thing resonating. We put together an MEscope model, and this is a pretty rough model, but it's that's all you really need for an application like this. But all the arrows on here, it's a little messy, but there are 357 measurements on the structural framework, which is a lot. Went up and down the boom for 4.5 of these units. There's a couple of beams in the 4.5 of these big beams. There's certain levels that we couldn't get to, but we got enough to get us the low frequency modes that we were interested in. This is the vortex shedding again. So here's my application, is one of the 6 beams, and it's moving like this. In my application, all 6 are doing the same thing. So they're all moving in the cross axis here. They're all in phase with each other. The whole structure is flexing that direction. So we have, and this was nothing operating. Unit was it was just forcing fluid through the tanks, and the wind was blowing. That's it. Now I've amplified this a lot so you can see this, but you'll see in a minute it may not be as bad as it looks. So it probably is doing something like this. I don't know if it's blowing past the cylinders that are giving me the problem or past the I-beams, because they'll get a different shedding frequency going on. But we'll see. This is that same mode. It's constructed at 152 CPM. That's about 2.5 hertz. So it was very close. We had 2 hertz before, but our resolution is much better with the accelerometers than it is with the camera. Picture's better on the other one. This one's better because it's put together from real data, not fake data. It's all empirical. So this is the first bending mode of the frame. The amplitudes, the worst amplitudes were 0.042 inches per second. If I'm looking at that, a foundation problem, and the foundation's moving at 0.042, I'm saying that's pretty good. My rule of thumb, anything above 0.05 starts you to get wondering, is there some looseness that's developing in a foundation? This number, this 0.042, was measured up here at the top of the structure, and it was still very small. So you basically go to 0 at the bottom, and these are all bolted together really well down into the base. And these are all free. So it's not nearly as bad. You are exciting a resonance. It has a mode shape. It takes very little input to give you that response, but it doesn't look like it's doing much right now. If we find out in the future with put our permanent monitoring up there, we can find out how bad it really gets and how much motion we expect at the top and how resonant it is. This is another mode, and this is a second bending mode. It's at 4.36 hertz or 262 CPM. The only thing really moving are these two middle columns. And instead of moving from the 0 at the bottom and to the maximum at the top, it's in the middle. So these things are basically doing a second bending mode. I don't know if I can get back to that or not. Hold on. There. So the second bending mode would look like this. So just a wiggle crossing over, and that's what we have there. Or it appears to be what we have. And that was this one, I believe. This is the third one I picked up. This is 381 CPM. There's 6.35 hertz. It's the first torsional mode. So if you look from the top, this thing would be twisting all over the place. I tried to use the same view all the time so it doesn't get confusing because it's a mess of beams in there. But there's a twisting mode. So from the top, everything's, or from the bottom, everything's still. This is the rigid body motion of the twisting or torsion mode. Amplitudes are on the order of 0.022, so just there is no amplitude, very small. This is the only one I couldn't make any sense of. This was occurring at 1185 CPM, so that's 19.75 hertz. This appears to be a 6-pole motor that's driving this frequency. A little slip, it's a 1200 RPM motor, basically. The amplitudes are on the order of 0.018, so still really tiny response. But you can see the beams, these three beams are moving in the same shape. So it looks like a second bending mode in the cross axis, or the longer axis. Conclusions, the analysis confirmed that concentrator tower was vibrating. Vibration analysis indicated low frequency rigid body motion of the frame structure. Traditional ODS vibration measurements were not elevated, but response suggested natural frequency modes that were being amplified by some source, and wind is the likely source. Potential sources of vibration were wind-related, flow-related turbulence from the process. Wind can create unstable turbulent flow around circular objects. This phenomenon is known as vortex shedding. Transition in the piping can also cause unique internal turbulent flow. I think the case for that is a little less because of what they're putting through. It wasn't that turbulent. Vibration measurements were cut short due to wind gust concerns. The man lift was wind rated near 28 miles per hour. The steady winds were greater than 21, and we really didn't know what the gusts were. So we decided we got up about 50 feet and said, nah, not today. So even with the winds, the structure didn't appear to be vibrating excessively. The reason we were there was because it probably was a windy day, but one of the lights on the tower was flickering. So it was probably just loose and moving in the wind, but you never know. There's mitigations to vortex shedding effects. Tall metal smokestacks or other tubular structures such as antenna masts or tethered cables can be fitted with an external corkscrew pin or a strake. This deliberately introduces turbulence, so the load is less variable and the resonant frequency won't be able to build. These are a few of the corrections. I'm not saying we should do one for this. It'd be a little more difficult and expensive since it's assembled already. There's a helical strake that you see on a lot of big towers. The problem with it here is we have insulation on all these lines. So you'd have to, I don't think this one would apply. This one, this shroud, might be a better choice. If this one has holes punched in it, I believe, some type of surface that doesn't let the air stream by, it'll make it more turbulent. These are a bunch of slots, which again probably won't work with the existing tower that we have. This one either is a variable fairing or a streamlined fairing. This is a splitter plate, so if you start getting vortexes, they can't interact with each other until they're farther downstream, and it won't excite the tower itself. There's ribboned cable, there's a pivoting guide vane, and there's some other spoiler plates where basically you can cut the wind generation down quite a bit, or the effects of the wind going past the cylinder. Okay. We'll try one more, see how far I get. It's about 135. I think I can squeeze it in. Oops. Sorry about that. This. Yeah, this is interesting. I still don't know much about it. I was given a job by a friend of mine. He was working in a power or a refinery down in Texas, and this was a tank and its agitation system. We didn't get a whole lot of input from the customer. The friend of mine, he took the data and sent it to me. He can't get anybody to tell him down there what the machine does, how it works, what the speeds are. I'm assuming that this is a motor direct coupled to possibly it's either a gearbox down here or a belt drive, and possibly a gearbox in here and a belt drive. Not sure, but it goes into the tank, relatively low speed, and this is just hanging off the bottom of the tank. But the big concern were all the erosion that's gone on over the years on these things. We believe that there's a couple of pedestals, one here and one back there, that are fairly identical. They've eroded that interface and it's actually lifting. So this concrete block is moving out of its foundation. Don't know what it caused it, nothing like that. I just have the symptoms and I'm looking to figure out what it is. So ODS video is perfect for this. This is the first shot. We can look at what's going on, and once it gets moving, you can see how all the plumbing lines follow. The two interesting things here, you can see this line opening up. So there's something wrong right off the bat in here. Yeah, it's not any good that you have fluid flowing under the corner as well. The hydraulic pump, this is a belt-driven pump back here, and the motor looks like it's pitching. So there's either a belt misalignment or a loose motor mount. And since they're both, the pump and the motor platforms are on the same block, they're just moving along with it as well. Other things of interest, there's distortion right here. Here's the shaft with a coupling on it. And this guard, I've noticed on a lot of machines, it doesn't do well with screens like this as far as animation. Don't know why yet. I'll have to figure that one out. By the way, every job I do with this thing, I learn more and more about different ways to think. Just like the little needle on the gauge might be the highest vibration, but it has nothing to do with what you're dealing with, the whole structure globally. So view number one, this is the FFT view. Remember, we can look at it in the time waveform or the frequency domain as well. So it shows a small motor issue with a belt drive and a loose foundation pedestal. I have another view. So basically they walked around and shot different views at the bottom of the tank and this motor gearbox structure. And in the background were things I was interested in. So here's that hydraulic motor or hydraulic pump. Here's the belt drive that drives it. And you're sitting on a block and you can see motion in the block between that and the floor. Another angle. More motion in the motor down here and the block lifting off. Just little piping motion in there. That's pretty normal. I had to process this a little bit differently. I had to remove some of the pixels or grid points because this was, I don't know what it was, just a plastic strap or something, and it was moving around. So it was the highest vibration. And here's probably another one I missed. This is would show a high vibration as well. This is the time waveform look at the same thing. So when I'm doing a frequency analysis, I remove all the background. So all this stuff, I keep this in the foreground so I can see what it's doing, and I move around this pedestal so that I can isolate this, and everything else in the background, the floor, the wall back here, all this piping, I can turn it off basically, okay? So it doesn't show up in the animation. See how this is all not moving it a bit. Here, I'm allowing it to move, but I'm looking for this base. So if I have a loose base here, I know what it looks like. This one, it should also be moving if it has a loose interface, and it doesn't appear to. So I have there and there are good. This one's shaking quite a bit, as we've talked about. This column here, it also has a little bit of a jitter to it. Okay, so that's in the time waveform. This is in the frequency response. So now, same thing, these blocks back here look good, and these are moving, but we're filtering to a certain frequency. That was another thing too. They didn't tell us what all the tooth counts, belt lengths, anything like that, even motor speeds. So we're kind of guessing at what frequencies to worry about in the spectrum. This is the time waveform of one of the blocks. Here's that hydraulic pump. Motors on the other side, you can't see it, but a lot of action going on. Okay, and a lot of motion in the piping. This is filtered to what I think is turning speed of something. It might be the hydraulic pump. But now there's a single frequency that we're pulling out. That's one of the dominant peaks, and you can see the loose foundation. And the last one's just behind the motor, or the agitator. There's the motor up there, and so forth. And we're looking at that. We're looking at the hydraulic system, how it's moving. And one of these videos, the friend of mine that sent it said this was vibrating, but I don't see it. Either it's in the wrong view here. It might be shaking in the view coming toward and away from the camera, but it doesn't look like it's going horizontal at all. This is some other stuff. This is miscellaneous vibration. I believe this is some type of sensor or light panel or something up here. I couldn't tell what it was. This is just a pipe that's shaking, and you can't even see this going when you're actually running if it's not enhanced like we have it here. So I'm interested in the foundation and then whatever else is going on, any potential fatigue problems. And that's, oh, we got one more. Maybe I got a couple more. This is previously, this is the time waveform version. So you can see everything kind of moving slightly, but nothing really bad. This is the frequency. So I dialed into these two frequency peaks, and they're moving. And that's all I have. Got 3 quick case histories, a lot of different camera stuff going on, different ways of looking at the vibration response in ways you wouldn't think is normal before. Now you're thinking, oh, wait a minute, I have a little dial on my dial indicator that's moving up and down more than anything else. So I'm gonna get a spectrum with a very high peak. And it has nothing to do with how good or bad the machine is. It's just a moving peak. I've had the same sort of thing. Somebody walks through the background while you're taking data. Somebody has a flashlight in a dark area and they're in the field of view. All kinds of things like that where it's not traditional vibration. It's just how the camera interprets what's going on in the field of view. We got any questions, Mark?
No questions at this point. If anybody has some, you want to go ahead and get those typed in to the box there. We can get your questions answered.
Can't believe it. No questions. Maybe they all fell asleep like you told them they were.
That's right. All right, here goes a few questions. Does it have to be an iPhone or can it be anything with 240 frame rate?
It doesn't have to be an iPhone. There are some Androids out there with slightly different frame rates, and the only difference is you type, if it's 260 frames per second instead of 240, you type that into the software, just so it knows the frame rate and what you're looking at. So they have a similar slow motion mode as well. I haven't used it. Some of the folks at Vibrant have looked at it before, and it seems to work just as well, if not better, on an iPad.
We've used an Android phone that I think went up to like 900 frames per second, which was extremely fast, and it certainly works just as well. So yeah, you're not limited on the type of camera per se.
Yeah. Well,
go ahead.
If you're a good analyst, you're going to prove that. So I've been doing a lot of that stuff. I'm trying out different things. That's one of the kind of fun parts of doing vibration work like this. It's stuff that you haven't seen before.
Another question here. Did you use extra lighting on the last problem?
I used absolutely no lighting whatsoever. And it is completely night and day, no pun intended, but I started out my vibration videos work. I brought all my light panels, all my tripods, and I could never get enough light on whatever I was looking at. Even outside on a sunny day was difficult because the aperture closes so much. You really lose it. I think what Mark was saying here, that 900 frames per second, that's probably starting to make things dark. I was doing 1,050 frames per second, something like that, with my high-speed camera, and I can get this. I can get all the frequency range I need with the 240, and it's you don't have to prepare any light panels, anything like that. Now I just carry them around and I never open up the box. Everything I do is on my iPhone.
James says we have actually used this recently on a cooling water tower, and it has been very revealing. Great stuff. Thank you, James.
Oh, good.
Appreciate that. Is there a duration?
Send a clip in, and we'll.
Yeah, there you go. Yeah, James, you want to send a clip in? We'd love to.
You'll be part of the next webinar.
That would be fantastic. The next comment here, question: is there a duration to collect data? Great question, David.
Duration.
I think I meant like 8 seconds, 2 seconds. Yeah, like
the
that.
high-speed camera. I was doing 8 seconds, and you don't really need 8. I think I proved in a bunch of trials that you need 2 to get good data for a high-speed 1,000 frame per second type application. But I usually take more. I take about 15 seconds of data for the phone. And there's that startup and shutdown of the camera when the speed is changing, when it's trying to go to 0 or it's trying to get up to 240. And I showed you in the first case history. That's what I'm trying to avoid. So I could get 5 seconds in the middle of a 15-second clip, and I won't see any of that start-stop stuff going on. And it works out great. And now they have Bluetooth starter controls. So I bought the last tripod I bought had Bluetooth controlled little module with it. So you can click start or stop and don't have to touch the phone. Because when you do touch the phone, you induce vibration, very high, low frequency vibration, because it'll bounce around before it goes back to zero again.
Okay, along those lines, what is the max frequency you can filter?
The max frequency would be half of the maximum frame rate, so it'd be 120 hertz. And you may say, well, that's not good enough. Well, if you're only looking at 2, 4, 6, 8, 10 pole motors, a 2-pole motor is 60 hertz or just less than that. You'll see 1 times and 2 times of that 60 hertz. So you don't want, you'll get all the data you need. Plus there's inside the software, there's something called order filtering. And you have a problem called aliasing in the camera. In your data collector, in your accelerometer platforms, you can filter it differently in the time domain. They have anti-aliasing filters, all these things that'll take everything above your Fmax and turn it to 0 for the most part. In other applications, what was I going to say? The aliasing filter. The orders filter inside the software can roll that back open, so you don't have 240 as your limit or 120. You can use all your range. I don't know how to explain it quickly without a picture, but it allows you to find the alias frequencies and filter those out for you. So you actually, the worst case, you get up to 240.
All right, next question from Georgie. Hopefully I'm pronouncing that correct. Do you ever work with videos sent by plant personnel, or do you always take your own videos? We certainly do.
This one was a plant person. The first one I did with the bearing, that was from a plant person. Both of them sent me something to look at. The one with the concentrator tower, that was a job that somebody asked me to do for them, somebody in the plant. So I'm getting quite a few jobs of just sending me a picture of your machine and send me some data from your camera. And I tell them what I think's wrong.
And Dan, how do they get a hold of you if they would like to send you a video?
Yeah, I should have that on the intro slide, shouldn't I?
That's okay. It's a very easy email. Yeah,
it's modalguy@aol.com. So modal, like modal testing, MODALGUY, modalguy@aol.com.
And you can always reach out to us directly as well. It's sales@vibetech.com, and we'd be happy to put you in contact with Dan. A couple more questions here. You guys actually did, this is James Dalton saying, commenting about the cooling tower. He said you guys actually did it here at ADM Southport. Is that something you may have done, Dan? I don't know. Maybe ADM Southport.
Well,
Archer Daniels, Midland. Yeah, that was Archer Daniels. That's right.
But I haven't been there. I have 2 other guys that work at ADM that work, well, they work for me, but they're different parts of the country in Iowa and Nebraska and what have you. Yeah, well, send me an email and let me know.
Yeah, James, if you want to get in contact with Dan, and we can work with you there. Could you show the movement in the last video again? This is coming from Keith. Sure, Keith, we could jump back there and hit the.
Yeah, I think this is the one he was talking about. 8. or doesn't want to go. Here we go.
Yeah, you can see the pipe shape.
Is this the one?
Keith, is that the right one?
Oh, yeah, it's the last video.
Okay.
There we go. So this is the FFT of the 8th video that I have in here. I don't know how many it was.
Yeah,
but
that's the right
showing
one.
what the piping vibration. And I don't know why that pipe's doing that.
That thing is bouncing all over the place.
But if you want to see these, give them a little processing time. Maybe check back with Vibrant tomorrow. And like Mark was saying, they have all the webinars on there.
Yeah, we'll get that spun up to the YouTube channel. Another question from Bob here. Can you send a summary of the aliasing frequencies? I think you showed a nice summary at a previous presentation.
Send it to you. Yeah, send me an email and I'll pull it out and email it right back to you. Yeah, and I was actually looking for that today. I was putting together my training class for ODS videos, and needed that one.
Do you remember what webinar that was that we did that one?
That was like two webinars ago.
Okay, so that probably would have been back in May.
Yeah, and
okay.
It was on aliasing.
Oh, right. Yeah, we did do a. Yeah, you can also, if for those of the rest of you guys, if you want to go back, you can take a look at that one. Again, back on the YouTube channel, there, I definitely know that one is up there. Great. Well, that about does it. I don't have any more questions here. Dan, any last words of wisdom you want to hand off to people?
Like take another 15 minutes. No, no. It just empirical thinking. You'll see stuff that you've never seen before, and it doesn't seem right. There's just work on explaining it. There's always a solution to the problem. That's all I have.
Good stuff. We'll get a few more of these going. I know these, like I said, these case studies are always very popular, and we always get quite a few attendees. So we will continue to do these. And if you have some other ones that you'd like us to take a look at, if you have some case studies that maybe you did yourself, or maybe you want us to do a further investigation on, shoot us a quick email, and we'd be happy to look into it and put together a webinar on it.
I do have one more thing. This was done with the accelerometers, right?
Oh,
the other one, this was all video. Okay, if I get the software, the ODS videos comes with the video software. It also comes with the accelerometer based 3-dimensional software. So there's ODS and then there's ODS videos.
There you go.
I always forget to say that.
Excellent. If you got any sales questions, feel free to reach out to us at sales@vibetech.com, and we can put together a quote for you if you're interested. Again, if you have any additional videos you want to send over to Dan, you can reach him at modalguy@aol.com. That's going to do it for us today. Stay tuned. We will get another one of these spun up next month, and we hope everybody enjoys the rest of your afternoon and have a great weekend. We will talk to you soon.